Today, we're embarking on a journey to one of the coolest and smartest factories in the world of woodworking. We're going to talk about how people looked at ordinary wooden floors, which fear moisture like a vampire fears garlic, and said, "Dude, we can do better." Thus, engineered hardwood was born. This isn't just a board, it's a true wooden club sandwich, a brilliant work of engineering where the beauty of natural wood is combined with superhuman stability. This is the story of how a floor that laughs in the face of humidity fluctuations is born from several different trees, a giant glue juicer, and an infernal ultraviolet tanning session. It all begins not with one, but with two different forests. The first forest is a runway for supermodels. Here grow those noble trees whose beauty makes the heart beat faster. Majestic oak, strong hickory, elegant maple, or luxurious American walnut. For our sandwich, we don't need the whole log. We only need its soul, its most beautiful part, the thin top layer that everyone will see. Therefore, the best, straightest logs are brought to the factory. First, a real spa day awaits them. They are immersed in huge pools of hot water, or placed in chambers where they are treated with steam at a temperature of 200 degrees Fahrenheit. This is done to soften the wood and make it ready for the thinnest slicing in the world. After this, the log goes to a machine that is something between a giant pencil sharpener and an industrial slicer for delicacies. This is a peeling or slicing machine. Imagine a sharp, scalpel-like knife 10 feet long. It is slowly brought to the rotating log and begins to shave off a continuous wide ribbon of wood, just 1/8 or even 1/16 of an inch thick. This is our veneer, our precious ham for the sandwich. This wet, flexible sheet is then carefully dried in special chambers to make it stable, but to preserve its natural beauty. But what will be the bread in our sandwich? For this, we don't need supermodels. We go to another forest, where simple workhorses grow. Fast-growing and inexpensive species like poplar, birch, or eucalyptus. These logs go through a similar peeling procedure, but the ribbons are cut a little thicker. And this is where the main secret of the stability of engineered hardwood begins. Imagine that you took several of these thin wooden sheets. You lay the first one so that the fibers run lengthwise. You lay the second layer on top, but you turn it 90 degrees so that the fibers run crosswise. The third, again lengthwise. The fourth, again crosswise. And so on, creating a multi-layered pie where each layer is perpendicular to the previous one. Why is this so important? Because wood is alive. It always tries to expand and contract across the grain, reacting to humidity. But when you glue these layers perpendicularly, they seem to hold each other in a steel embrace. One layer wants to expand, but the other, lying perpendicularly, does not allow it to do so. This is a brilliant solution that makes the base of engineered hardwood incredibly stable and resistant to deformation. This multi-layered pie of cheap wood is sent under a hot press, where under huge pressure and temperature, it is glued into a single, strong block, like plywood. These are the muscles of our floor. Now it's time to assemble our club sandwich. We have the sole, a thin, beautiful veneer of expensive wood. And we have the muscles, a thick, stable base of cheap wood. They need to be connected. The base moves along a conveyor and passes under rollers that resemble giant paint rollers. These rollers generously pour a special, incredibly strong glue onto it. Our precious veneer is carefully laid on top of this sticky surface, and this whole structure is sent to the final hot press. With a force of hundreds of pounds per square inch, the press connects beauty and strength into a single hole. At the exit, we get a huge master sheet, from which individual boards will then be cut. But this is not a floor yet, it's just a blank. It's time for makeup and a manicure. Giant saws cut the large sheet into individual boards of standard width, for example, 5 or 7 inches. And here, each board goes to one of the most important machines, the milling machine. An incredibly complex system of mills and knives, rotating at a frantic speed. On one side of the board, they cut a long protrusion called a tongue, and on the other, an equally long groove called a groove. It is this system that will allow the boards to fit together perfectly during installation, forming a continuous, smooth surface without gaps. Now our board has the correct shape, but its surface is still a bit rough. It is sent for sanding. This is a whole line of several sanding machines, each of which uses finer and finer sandpaper. After this process, the surface of the board becomes as smooth as silk, ready for the final coating. And here, the real high-tech begins. The board enters a finishing line that looks like a car wash, only instead of water and soap, there is varnish and ultraviolet light. First, rollers apply the first layer of a special, incredibly durable varnish based on aluminum oxide. This is one of the hardest substances in the world, which makes the floor resistant to scratches. Immediately after application, the board passes under powerful ultraviolet lamps, and the varnish, which in normal conditions would dry for hours, hardens in a fraction of a second under the influence of ultraviolet light. Then a second layer is applied, and again a tan under ultraviolet light. The third, fourth, fifth. Sometimes it goes up to 7 to 9 such layers. As a result, we get a perfectly smooth, incredibly strong, and durable coating. That ultraviolet coating is not just a varnish. Aluminum oxide is added to its composition, one of the hardest minerals in the world, second only to diamond. From 7 to 9 layers of this coating are applied to the board, and each layer is instantly baked by ultraviolet light. As a result, we get a surface that is many times more resistant to scratches and wear than a traditional varnish applied to a solid board after installation. At the final stage, each board undergoes strict quality control. Inspectors with an eagle's eye look for any defects, scratches, uneven color, problems with geometry. Only perfect boards get a ticket to life. Robotic manipulators carefully stack them in boxes, indicating the type of wood, color, and dimensions. And so, having passed the path from 2 different forests, through hot baths, sharp knives, sticky waterfalls of glue, and an infernal ultraviolet tan, this brilliant creation is born, engineered hardwood. It took the best from nature, its beauty, and the best from engineering, its stability, to become the perfect floor for our homes, which is not afraid of either winter dryness or summer humidity. The engineered hardwood market in the USA is a giant that turns over more than $10 billion a year. And this is not just a stable market, it is growing rapidly, winning an increasing share from its older, solid brother, solid wood. Why? Because it's smarter, and the numbers prove it. The main superpower is stability. Thanks to its cross-layered, multi-layered structure, engineered hardwood is 50 and even 60% more stable than a solid board of the same species and thickness. What does this mean in real life? It means that it can be installed where ordinary wood would go crazy from humidity fluctuations, in basements, kitchens, bathrooms, and on a concrete slab. It is not afraid of underfloor heating. If one perfect log of precious white oak was sawn into a 3/4 inch thick solid board, a certain number of square feet of flooring would be obtained. And now, attention! If this same log were used to produce thin veneer for engineered hardwood, 3 or 5 times more finished flooring could be obtained from it. This means that to cover the same area, 3 or 5 times fewer valuable trees need to be cut down. This makes engineered hardwood a much more environmentally responsible choice. Every year, over 500 species of bamboo are grown worldwide, and China holds the richest treasure of them all. Imagine this: 16 million acres of lush green forests, an area larger than all of West Virginia, pulsing with life and growing so fast you can literally watch it with your own eyes. Some species can shoot up more than a meter in a single day. This is where a $27 billion industry begins, an industry that feeds, clothes, and even builds entire cities. But behind this green marvel are secrets you've likely never seen. Watch closely. If you stay with this video until the end, you'll discover something that will make you see this simple grass in a completely new light. China is the undisputed king of the bamboo world. The country is home to over 500 bamboo species, and its bamboo forests cover more than 16 million acres. That's more land than all of West Virginia, covered entirely in a sea of green. This massive natural resource is the foundation of a multi-billion-dollar industry. China produces 80% of all bamboo products in the world, exporting them to more than 100 countries. It all starts not in a noisy factory, but in the silence and greenery of endless bamboo forests stretching across southern China. Standing in the middle of one, you're surrounded by thousands of smooth, perfectly straight trunks, reaching more than 100 feet into the sky. Sunlight barely filters through the thick leaves, casting a mystical green glow. And the only sounds are the soft whispers of wind and the gentle creaking of stalks brushing against each other. But bamboo's real superpower is its outrageous, almost indecent speed of growth. It's the rocket engine of the plant world. Some species, like the giant moso bamboo, can grow 3 feet in a single day. Imagine that. You could literally sit and watch it grow. In just a few months, a young shoot reaches full height. It's not a tree that takes decades. It's a giant grass ready for harvest in just 3 to 5 years. And here's the best part. When you cut one stalk, the root system stays alive and immediately sends up new shoots. This isn't deforestation. It's more like mowing a lawn, an endless, self-renewing resource. When harvest time comes, workers enter the forest. There are no roaring chainsaws or heavy machines tearing up the ground. Most of the bamboo is cut by hand, using simple saws or machetes. With a dry crack, the stalk falls to the ground. The branches and leaves are trimmed off, and the smooth, hollow green stems, called culms, are tied into bundles and carried out of the forest. This is the raw material, the uncut gem that's headed to the factory to be transformed into 1,000 different things. Bamboo is a true superhero in the fight against climate change. It absorbs carbon dioxide 35% more efficiently than most trees and produces 35% more oxygen. These 16 million acres of bamboo in China are giant green lungs working to clean the atmosphere. It doesn't need pesticides or fertilizers, making it one of the cleanest crops to grow. And unlike cotton, one of the thirstiest plants in agriculture, bamboo thrives on rainwater alone. Let's look at 2 of the most fascinating transformations. First, how do you turn a round, hollow stalk into a hard, flat floorboard tougher than oak? The bamboo trunks are first cut into sections and fed into a machine that splits them into long, narrow strips, like a giant apple slicer. These strips still have a curved shape and outer skin. So they go through another machine that shaves off the outside and inside, turning them into perfectly rectangular slats. Next comes a spa treatment. The slats are boiled in hot water or steamed. Not for cleanliness, but to remove all the sugars and starches that bugs and mold love to feed on. After that, the sugar-free slats are placed in a drying kiln, where they're slowly and carefully dried to a precise moisture level. Now we have thousands of perfectly dry, sturdy slats. Time to put them together. The slats are coated with glue and stacked into a mold, where a massive hydraulic press comes down. With a force of thousands of pounds per square inch and high heat, it compresses the slats into a solid, monolithic block. From this block, manufacturers cut floorboards, countertops, plywood, and even structural beams. The second transformation is even more astonishing. How to turn this tree-like grass into soft, silky fabric for a shirt or bed sheets. This is industrial alchemy. The bamboo culms are first chipped into small flakes. Then, the flakes are soaked in a chemical solution, usually caustic soda, that breaks down the cellulose, the plant's rigid framework. After several hours of cooking, the hard chips become a soft, thick mass that looks like paper pulp. This pulp is washed, bleached, and pressed to squeeze out excess moisture. What's left is a sticky, dense gel. This gel is then forced through microscopic holes in a metal plate called a spinneret, like a giant molecular meat grinder. On the other side emerge ultrafine, continuous threads. These threads drop into a bath of another chemical, usually sulfuric acid, which instantly solidifies them. Now we have silky, shiny fiber, bamboo viscose. It's washed, dried, and spun into yarn, which is then woven into incredibly soft, breathable, and hypoallergenic fabric. Now let's peek into the world of small eco-heroes. The birth of a bamboo toothbrush. It all starts with harvesting mature 4-year-old moso bamboo. The trunks are cut, then sawed into long, even sections. These sections are split into thin slats. Next, the slats are run through a special milling machine. Imagine a high-precision pencil sharpener. It shaves the slat into a perfectly smooth, rounded stick, the future handle. This process is incredibly fast, with thousands of handles flying out every hour. Then comes heat treatment. They're baked to make them more water-resistant and to give them a beautiful caramel tone. Next step, the haircut. A machine drills dozens of tiny holes into each handle with surgical precision. Then comes the most fascinating part, bristle implantation. A machine, similar to a high-speed sewing machine, grabs a bunch of nylon or biodegradable bristles, folds it in half, and punches it into each hole using a tiny metal staple like an anchor. This happens dozens of times in seconds. The final touch, trimming. All the bristles pass through a trimmer to make them perfectly even or shaped. And that's it. Simple, brilliant, and much kinder to our planet. But these are just 3 examples. This green dragon has 1,000 faces. Young bamboo shoots are a delicacy in Asian cuisine. It's used to make billions of chopsticks, cutting boards, dishes. It's burned to create activated charcoal for filters. It becomes paper, blinds, furniture, even computer mouse shells. In construction across Asia, it's still used as incredibly strong yet lightweight scaffolding for skyscrapers. And this entire ecosystem, from the farmer cutting stalks to high-tech fabric factories, creates a $27 billion economic phenomenon. But what does that mean? That's more than the GDP of some small countries, like Iceland or Jamaica, and the number keeps growing. Just 10 years ago, the industry was half the size. Projections suggest that by the end of this decade, the global bamboo market could exceed $100 billion, and China plans to stay its dominant player. This isn't just about a few big factories. It's an ecosystem that supports over 35 million people, from rural farmers to designers in Shanghai. It's a story of how nature's wisdom, multiplied by human ingenuity, can turn ordinary grass into an infinite resource that dresses us, feeds us, and builds our world. Every year, over 25 billion square feet of oriented strand board are produced worldwide. Imagine, this amount would be enough to cover the entire state of Delaware. Twice. Or to build a path around the Earth over 190 times. Plywood was once the king of the market, but the 80s changed everything. And today, OSB controls over 75% of American construction. But how is a material that changed the industry forever, born from young trees, through hot baths, giant graters, and infernal presses? Watch closely. At the end, you'll learn a secret that even builders keep quiet about. It all begins not in a waste warehouse, but in the forest. For the production of high-quality oriented strand board, preference is given not to random offcuts, but to whole logs, usually from relatively young, fast-growing trees like aspen or southern yellow pine. These forests are often managed and self-sustaining, which makes the process more environmentally friendly. When the logs, tens of feet long, arrive at the factory, they are not immediately sent to the workshop. First, a hot bath awaits them. They are immersed in long pools of hot water, or placed in chambers where they are treated with steam. This isn't just washing. This process, which lasts several hours, softens the wood and, most importantly, weakens the bond between the wood and the bark. After this sauna, the logs go to a debarking machine. Imagine a huge rotating drum with protrusions inside. The logs rubbing against each other and against the walls of the drum, and the bark flies off them like a husk. Bark removal is a critically important step, as bark lacks strength and does not glue well, so it is an undesirable impurity in the final product. Annually, factories in North America produce over 25 billion square feet of oriented strand board. This number is so absurd that it's hard to comprehend. Let's try. If you took all this quantity of panels and laid them out, you could completely cover the entire territory of the state of Delaware. Twice. Or build a continuous 1-foot wide path that would wrap around the Earth at the equator over 190 times. This is not just a lot, it's total domination. For decades, plywood was the king of the market. But in the 80s and 90s, this daring newcomer came onto the scene, and today oriented strand board controls over 75% of the sheathing market for walls and roofs in residential construction in the United States. This was a real quiet revolution. The cleaned, light, and still damp trunks are ready for the main event, transformation into thousands of thin ribbons. They go to a machine called a strander, or a flaker. This is the heart of the whole process. Imagine a giant metal disc rotating at a frantic speed, equipped with dozens of sharp, scalpel-like knives. The log is slowly fed to this disc, and it shaves off long, flat, chip-like ribbons, strands. This is not chaotic shavings. Each strand has parameters precisely set by engineers. The length can reach 6 inches, the width about an inch, and the thickness only a few hundredths of an inch. It is this geometry, this noodle shape, that is the key to the future strength of the oriented strand board panel. When ordinary boards are made from a log, a significant part of it, up to 50%, turns into sawdust, offcuts, and shavings. And in the production of oriented strand board, from 85 to 95% of the entire wood of the log is used. We will talk about this later, but practically nothing goes to waste. The strands are cut from the entire length, and the bark, sawdust, and the smallest particles are burned in furnaces to provide energy for the factory itself. This makes this material not only cheaper, but also much more environmentally responsible. The resulting mass of wet, fresh chips, resembling a huge pile of light noodles, is stored in special bunkers, and from there, it is sent for drying. This is a huge, multi-story drum, slowly rotating, half a football field long. Inside it, a high temperature is maintained, and while the strands are slowly tumbling, moving from one end to the other, a stream of hot air evaporates the excess moisture from them. The moisture needs to be reduced from 50 or 70% to only 2 or 3%. This is absolutely necessary so that the resin can properly soak the wood and glue it firmly. After drying, the strands pass through a system of huge vibrating screens, which sift out particles that are too small, for example dust, which will go to fuel for the same dryer, and pieces that are too large, which will be sent for regrinding. Now the perfectly dry and sorted strands are ready for impregnation. They enter a huge, slowly rotating drum mixer. While they are being mixed, a sticky chemical cocktail is sprayed onto them through special nozzles. The main ingredient is a waterproof resin, which will be our glue. The second important component is paraffin wax. It envelops each chip like an invisible raincoat, and it is this that will give the future-oriented strand board panel its famous moisture resistance. And now, the smartest and most important part of the process begins, which gave the material its name, orientation. The strands, impregnated with glue and wax, go to a long, wide-forming conveyor. Here, a whole system of mechanical choreographers works. Special discs, rollers, and combs that lay out the chips in a precisely defined order. First, the bottom layer is formed. The choreographers lay out the strands so that they all lie parallel to the long edge of the future panel, that is, lengthwise. Then comes the turn of the middle layer. Here the strands are laid out perpendicularly, that is, crosswise. And finally, the top layer is again laid out lengthwise. As a result, we get a thick, fluffy, 3-layer pie, where the fibers in each layer are perpendicular to the fibers in the adjacent one. It is this cross structure, which imitates the strength of plywood, that is the secret that makes oriented strand board incredibly strong in bending and resistant to deformation. This fluffy mat, which can be several feet thick, slowly moves to the final test, the hot press. This is a real industrial leviathan, a multi-story structure that creates colossal pressure and heat. The mat enters inside, and massive steel plates begin to compress it with a force of hundreds of pounds per square inch. At the same time, the press is heated to a temperature of 400 degrees Fahrenheit. This heat activates the resin, causing it to polymerize and permanently glue all the chips into a single monolithic shield. The wax also melts, even better impregnating the wood and filling microscopic voids. In a few minutes, the loose mass turns into a hard, incredibly dense, and hot panel. A huge master sheet comes out of the press, which can be 50 feet long and 12 feet wide. While it is still warm, its edges are trimmed with diamond saws, and then giant saws cut it into standard building formats, most often 4 by 8 feet. Markings with information about its thickness, class, and compliance with building codes are applied to the surface of the panel. Sometimes, special tongues and grooves are cut into the edges so that the sheets fit together perfectly when installing a floor or roof. The finished, perfectly rectangular sheets are stacked in high piles by robotic manipulators, wrapped in protective film, and sent to the warehouse. And so, having passed the path from a whole log through a giant grater, a sticky shower, and the fiery embrace of a press, this honest, unpretentious, and insanely strong material is born, ready to become the silent but reliable foundation for thousands of homes across the country. For the construction of an average single-family home with an area of 2,400 square feet, approximately 8,000 square feet of oriented strand board panels are needed. This material goes into everything. They sheathe the exterior walls, creating a strong and rigid frame. They make a solid sheathing on the roof, on which shingles are then laid. And of course, they make the subfloor, which is the foundation for all rooms. In essence, the entire modern American house is a wooden frame wrapped in a strong cocoon of oriented strand board. Every year, over 1 billion square feet of laminate flooring are sold worldwide. We see this covering every day at home, in offices, and even in shopping malls. But few people realize the complex engineering hidden in each plank. Imagine, under a pressure of over 1,000 pounds and at a temperature higher than 400 degrees Fahrenheit, thin layers of paper and resin are transformed into an ultra-durable surface that challenges stone itself. The laminate market is valued at tens of billions of dollars, but behind these numbers is a process that is impressive in its scale and precision. Watch until the end, and you'll discover the secret that your floor is hiding. Laminate, which has become an extremely popular choice for flooring, combines aesthetics, durability, and cost-effectiveness. Its production begins with the careful selection of raw materials and ends with the creation of finished panels, ready for installation. For the manufacture of laminate, 4 main components are used: the substrate, a stabilizing layer, decorative paper, and a protective layer. Each of these elements plays a key role in the formation of the final product. The process begins with the preparation of the core, or the base of the laminate, which is the most important part that provides its strength and stability. This core is made from a high-density fiberboard, known as high-density fiberboard. The production of HDF begins with sawing wood, mainly coniferous species, into small chips. These chips then undergo a steaming and cleaning process to remove foreign impurities. After this, the wood is transformed into fibers using special mills. The resulting fibers are mixed with glue, most often based on synthetic resins, and formed into a thick, soft mat. Next, this mat undergoes hot pressing under a pressure of about 700 pounds per square inch at a temperature of 400 degrees Fahrenheit. This pressing compacts the fibers, forcing out moisture and air, and creates a strong, uniform HDF board. The thickness of such boards is usually from 1/4 of an inch to 1/2 an inch, depending on the laminate class. The quality of the board directly affects the moisture resistance of the finished laminate, its bending strength, and overall durability. The next important stage is the preparation of the decorative and protective layers. The decorative layer is a special paper on which a printed pattern is applied, imitating wood, stone, or another material. This paper is impregnated with melamine resin, which, after polymerization, gives it hardness and wear resistance. The protective or overlay layer is also paper, but it is impregnated with an even greater amount of melamine resin and small particles of aluminum oxide. Aluminum oxide, which is a very hard material, gives the laminate its main property: resistance to abrasion and scratches. The thickness of the protective layer is only a few thousandths of an inch, but it performs a critical function. Both of these impregnated paper layers are dried and stored in rolls until the pressing moment. The third layer, the stabilizing or balancing layer, is placed on the lower side of the base. This layer also consists of paper, impregnated with resin, and serves to prevent the board from warping. Without this layer, during use, the difference in pressure and humidity between the upper and lower layers of the laminate could lead to the panel bending. The stabilizing layer helps to maintain the geometric stability of the board. The key moment in the production of laminate is the hot pressing process, which combines all 4 components into a single monolithic panel. This takes place on multi-layer presses, where the prepared sheets are assembled into a sandwich. First the stabilizing layer, then the core. After that the decorative layer, and on top, the protective overlay. This multi-layer structure is placed in a press where, under the influence of high temperature, which can reach 420 degrees Fahrenheit and a pressure of 1,200 pounds per square inch, the melamine resins melt and harden, securely bonding all the layers together. This process takes from 30 to 40 seconds and is called lamination. During pressing, the surface texture is also formed, which can imitate the texture of wood. After pressing, the laminate sheets are cooled and stabilized, which is important to prevent deformation. When the panels have cooled, they are sent for trimming and milling. At this stage, the large sheets of laminate, which can be 8 feet by 4 feet in size, are cut into smaller, standard-sized panels. For example, 48 inches by 6 inches. After trimming, locking joints, known as a click system, are milled on the side edges of each panel. This is a key feature of modern laminate, which allows it to be laid without using glue. The milling process must be extremely precise to ensure a perfect connection between the panels. Tolerances are only a few thousandths of an inch. The final stages of production include quality control and packaging. Each batch of laminate is tested for abrasion resistance, impact resistance, moisture resistance, and other parameters. The abrasion resistance test, known as the Tabor test, determines the wear class of the laminate. A high class means that the laminate will withstand a greater number of abrasion cycles. After successfully passing all tests, the panels are sorted, packed in sturdy cardboard boxes, and prepared for shipment. The weight of one box can be 40 pounds. All these processes, from the transformation of wood into fibers to the packaging of finished panels, are part of a highly automated and technologically complex production cycle. The result is a laminate that not only has an attractive appearance, but also high performance characteristics, which makes it one of the most popular flooring options in the United States and around the world. The total length of a production line can reach hundreds of feet, and the production speed is measured in thousands of square feet per hour. Understanding these processes helps to appreciate the complexity and engineering excellence of the product that we see every day in homes, offices, and commercial spaces. The global laminate flooring market has shown stable growth in recent years, driven by its popularity as an affordable, durable, and aesthetically attractive covering. According to expert estimates, it is projected that by 2030, this figure will grow to $35 billion, demonstrating an average annual growth rate of about 4%. The main driving factors are the construction boom in developing countries and the growing popularity of do-it-yourself repairs in developed countries. The geography of production and consumption. The largest regions for laminate production and consumption are the Asia-Pacific region and North America. In the United States alone, the annual production of laminate reaches billions of square feet. Europe also remains a significant player in the market, but the growth rates there are somewhat slower. Approximately 40% of the global demand for laminate comes from the residential sector, while the remaining 60% is from the commercial and industrial sectors. A significant amount of wood raw material is used for the production of laminate. Typically, to produce 1 square foot of high-density laminate board, approximately 0.15 cubic feet of wood is required. Given the production volumes, this leads to significant consumption of forest resources, although most manufacturers use recycled wood or waste from the sawmill industry. Standard sizes of laminate planks in North America range from 48 to 60 inches in length and from 5 to 8 inches in width. The weight of one package can be from 35 to 45 pounds, depending on the thickness and density of the material. In the modern market, there is a growing demand for laminate with a high imitation of natural wood and stone. Over 70% of sales are for decors that imitate wood, with oak and maple shades being the most popular. The demand for water-resistant laminate is also growing, which occupies over 25% of the market and continues to increase its share, especially for use in kitchens and bathrooms. The next time you walk on your laminate floor, remember this epic story. So enjoy your renovated space. Every year in the United States, hundreds of thousands of tons of sheet piles are driven into the ground. That's so much steel that it would be enough to build several aircraft carriers. Imagine, these metal giants don't rise up into the sea but disappear underground, holding our cities, dams, and ports from destruction. But how is a perfect steel profile, with a tolerance smaller than the thickness of a fingernail, born from a pile of old scrap? What happens in the furnaces with 3,000 degrees and on the rolling mills, where metal is formed at the speed of a car? Watch until the end, and you will discover the secrets of production that are usually hidden from prying eyes. Annually in the United States, hundreds of thousands of tons of these profiles are produced and driven into the ground. To imagine this weight, think of an aircraft carrier. One such ship weighs about 100,000 tons. This means that in a year, the country creates enough sheet piles to build several such steel floating cities. This is an endless stream of metal that goes underground to hold what is on the surface. It all begins, as in many stories about steel, at a huge scrap metal yard. This is a place where old ships, building structures, and industrial junk get a chance for a new, noble life. A giant crane with an electromagnet gathers tons of this metal and loads it into a huge ladle, which is sent to the melting shop. There, in the roaring hell of an electric arc furnace, where the temperature reaches 3,000 degrees Fahrenheit, this scrap is transformed into a boiling lake of liquid steel. Special alloying elements are added to this melt so that the future pile is not only strong, but also resistant to corrosion, as it will have to work for decades in moist soil. Next, this fiery river passes through a continuous casting machine, where it cools and solidifies, turning into a long, red-hot steel billet called a slab. This is our blank, our formless piece of dough, in which all future strength is already embedded. These hot slabs, cut into pieces of the required length, are sent to a reheating furnace. There, in a controlled heat, their temperature is again brought to the ideal plastic state, about 2,200 degrees Fahrenheit. They become soft and pliable, ready for the main transformation. And now the most interesting part begins: rolling. The red-hot slab comes out of the furnace and enters the rolling mill. It's necessary to form not just a symmetrical profile, but a complex shape with bends and, most importantly, with a perfect lock on the edges. The rolls of the rolling mill for sheet piles are not just cylinders. They are real sculptors of steel, having complex shaped grooves. The slab flies into the first pair of rolls with a roar, which squeezes it and begins to form the main profile, usually Z-shaped or U-shaped. Then it passes through the next pair, which further refines the shape. And so, step by step, passing through dozens of such rolls, our flat bar is transformed into a long, ribbed ribbon before our eyes. We talked about locks or interlocks. Well, the tolerance in their manufacture is only a few hundredths of an inch. That's less than the thickness of a fingernail. The red-hot steel ribbon flies along the rolling mill at the speed of a car, and at this moment, the rolls form a lock on it with such incredible precision. This is necessary because at the construction site, workers will have to connect hundreds of such piles. If the tolerance is even slightly larger, this giant industrial zipper simply won't close. On average, 1 square foot of a sheet pile wall weighs from 20 to 40 pounds. And now imagine one pile 60 feet long. Its weight can easily exceed 3,000 pounds. This is like the weight of a small sedan, concentrated in one long, thin piece of steel. And these piles, interlocked together, form a wall capable of withstanding the pressure of earth and water, equivalent to the weight of dozens of trucks pressing on it simultaneously. But the most important thing happens at the edges. The last sets of rolls, finishing rolls, form the most complex element of the pile, the lock or interlock. On one edge of the pile, a groove is formed, similar to clasped fingers, and on the other, a protrusion, similar to a thumb. These elements must be formed with an accuracy of a fraction of an inch. If the lock is too tight, it will be impossible to connect the piles at the construction site. If it is too loose, the wall will not be sealed and will leak water. Therefore, the rolls with incredible force, but at the same time with precision, press out this complex profile along the entire length of the red-hot steel ribbon, which can reach several hundred feet. The hot, perfectly formed pile crawls out of the last roll and along a roller conveyor goes to a cooling table. There, slowly cooling, it acquires its final strength. After cooling, it is checked for straightness and, if necessary, straightened on a special straightening machine. Then it's time for the final operations. A huge cold saw, with a deafening roar, cuts off piles of standard length from the long ribbon. Inspectors take special templates, or gauges, and carefully check the geometry of the locks. They check whether the fingers and groove fit perfectly, whether there are any defects that could prevent connection. This is a guarantee that, at the construction site, somewhere in a deep pit, these steel sheets will connect into a single, strong, and waterproof wall. Some piles may undergo additional processing. A special sealant is applied to their locks, which, when connected, fills microscopic gaps, making the wall completely sealed. The finished checked piles are collected into bundles, marked, and loaded onto railway platforms or barges by giant cranes. And so, these steel soldiers, born in fire and pressure, are ready to set off for their service, to go underground and silently, invisibly to all, bear the weight of the earth and the pressure of water, making the construction of the most daring modern projects possible. The lion's share of sheet piles is used in marine infrastructure, the construction of ports, piers, docks, and breakwaters. They are the silent guards of our coastlines. A huge number go to flood protection, forming the core of dams and levees along rivers, especially in places like New Orleans. And of course, they are indispensable in large cities, where a deep pit needs to be dug for the foundation of a skyscraper, right in the middle of dense development. This steel wall, driven into the ground, prevents neighboring buildings from sliding into the pit. So these hundreds of thousands of tons of steel are not just production statistics. They are a measure of our ability to tame the land and water, to build where it was previously impossible, and to protect our cities from the elements, one precise lock at a time. The finished piles lie in neat bundles, resembling giant packs of pencils. The first move is made by overhead cranes. A huge beam moves under the ceiling of the workshop. Powerful electromagnets or special traverses with several hooks hang from it. With a hum, the crane descends, and with a metallic clang, it picks up a whole bundle of piles, which can weigh 30 tons. The crane operator transports this cargo and carefully places it on a transport vehicle. And here we have two main paths, by land or by rail. If the construction site is relatively close, the piles will go by truck, but these are not ordinary semi-trucks. To transport 60-foot piles, special extendable platforms are needed. This is a very long trailer that can extend like a telescope, reaching an incredible length. Due to the length of the cargo, the driver needs incredible skill to navigate turns. Often, such cargoes are accompanied by special vehicles with flashing lights, which warn other drivers and help in difficult sections. Every turn at an intersection is a slow, calculated maneuver that requires all the available space. If the distance is long and the order volume is huge, the railway comes to the rescue. Bundles of piles are loaded onto long, flat car wagons. This is much more efficient for large batches. An entire freight train, loaded with hundreds of tons of steel piles, looks like the spine of some prehistoric beast. With a rhythmic clatter of wheels, it travels hundreds of miles, crossing states, to deliver its cargo to the station nearest the construction site. There, the piles are reloaded onto trucks for the final throw of a few miles.